Hi, today we are going to go through vision system training number 2. We have 4 topics to go through. First, hardware and the software. We'll take a brief look at the hardware and the software, and we'll also look at the normal setup procedure. Number 2, the most important and the basic concepts and the tools, including grayscale, histogram, blob, pattern, region, and the find line tool. We'll also look at the 3 most important major parts in our vision programs, including exposure adjustment, location search of the features, and measurement method to determine pass and fail. Finally, we'll look at the style or type of our vision programs. Our vision programs can classified into 3 types. Based on identification method, based on inspection ID method. So one type is a no ID method. The second one is a pattern-based ID method. The third one is a counter-based ID method. The major components in our Cognex camera-based vision system include inside cameras, inside input-output module, LED light, and a personal computer. Cognex has different series of cameras. We use the inside cameras. And some of them have integrated LED light. So for those camera, you will usually expect a flashlight for each picture. And the input and output module is the inside CIO micro module. It is essential. The camera and the I/O module are connected by cable, and the camera does not directly connect to the computer. Instead, the computer has a Ethernet cable connected with the I/O module. The LED light is controlled by the robot for light on and off. And there are communication signals between robot and the I/O module. So the robot also send the light on and off signal to the I/O module and the camera trigger signal. And on the other hand, the I/O module send a pass-fail signal to the robot and the vision completed signal as well. The software we're using is the Insight Explorer software. There are different versions on our computers. Right now, the highest version we're using is this version, which is released in 2019. Now let's take a quick look on how to use Cognex vision system in our setup procedure. A working instruction is available as document SU24 on the shared driver in this folder. So soon after you turn on the computer, the software should launch itself. If it doesn't launch, you can click on the Insight Explorer icon to launch the software. Once the software is launched, it looks like this. There are 2 views in the software. One is the Easy Build view, which it looks like this, and the other one is spreadsheet view. So if it is an Easy Build view, then you can change it to a spreadsheet view by clicking on this menu and then select spreadsheet. Well, you will see a network palette in this area. If you don't see that network palette, you can click on this network palette icon to let this information show up here. So usually the camera should show up here. There can be one or more cameras and also computer icons here. So please make sure you select the right camera. Okay, select the correct camera for this station, for the current station. So the first thing you want to do is to connect it to the camera. So the way to do that is to double click on the camera icon. In some case, if the camera icon does not show up, then for instance, if it looks like this, and there's only computer icon and no camera icon here, and then either there is no camera connected to this computer, or the camera is connected, but however there is some communication problem. So in this case, then to solve this problem, you can power cycle the camera, and then the camera can show up. So let's come back to see. Here, I would like to show you more. Okay, this is the icon for Insight files. So click on this icon, then there is another palette shows up. Typically, if you highlight on a camera, then the vision programs in the camera will show up listed here. Okay, and there are other icons. This one is to turn on or off the spreadsheet view, and there are these icons to zoom in or out the image. Okay, and this is the icon to change the status to online or offline. So now this is highlighted, and then it is online, and then click again, and then it can go to offline. So when we do programming or edit a program, we need to go offline, and then when we want to run a program, then we can go online. Okay. So when you want to run a program, we have just mentioned that you need to just pull this the right program and then drop it into the spreadsheet view area. Okay, so make sure you select the correct program corresponding to the current mode number to run. Okay, so we haven't looked at this icon yet. This one is the custom view icon. So turn on this icon, then you can see a custom view like this. Here is overlay icon. So turn on this icon will show like the mode number, pass fail information, and the overlay marks over. There are some basic concepts and tools that are very important to go through. The first one is grayscale. To understand the grayscale, we'll start from pixel. Vision system deals with digital image. And then pixel is the smallest unit to represent a digital image. If we zoom into an image to the maximum extent, you will eventually see pixels. The color of a pixel can be black, can be white, or can be a gray color in some level between black and white. And so a digital image actually is a 2D array of pixel values representing light intensity. For black and white images, such values are called grayscale values or gray levels. Then in a computer, the color or the gray level of each pixel is memorized or is represented by 8-bit data. So for an 8-bit data, there are 8 bits, and then in a computer system, each bit can either be 0 or 1, can have two status, either be 0 or 1. And if every bit is 0, then the gray level value is 0, and it represents black color. If every bit is 1, then the gray level value is 255, which is the highest, and then it is a white color. Then there are different combinations between all 0 and all 1, between 0 and 255. So they can represent different gray level. So for an 8-bit data to represent the color of a pixel or the gray level of a pixel, there can be 256 levels. Okay. Now that an image can be represented with pixels of certain gray levels between 0 and 255, we can go ahead with the concept of a histogram. Let's assume we have 256 beings corresponding to the 256 gray levels, and distribute those beings along the horizontal axis in order. We can now place each pixel into the corresponding beings. Once we have distributed all the pixels of the image, we can count the number of pixels in each being, and then form a chart like this. This axis represents the number of pixels. So this forms a chart of a histogram. And so the histogram is a frequency distribution, shows how often at each different grayscale value the pixels are distributed. And now we can take a look at the concept of threshold. If we observe the shape of a histogram, it typically has one or more peaks. Okay, suppose that there are 2 peaks. So one is the bright group, and the other is the darker group. So we can divide them into 2 groups by assume a value which is called a threshold. So anything brighter than the threshold is considered to be white. Anything darker than the threshold is considered to be black. So an image that can actually be converted into black and white by assuming a threshold. We can also take a look at the average. The average actually is calculated by summing the grayscale values for all the pixels in a specified range, and then divided by the total number of pixels in that same range. And now let's quickly take a look at the contrast. So assume like we have this brighter group and a darker group, and there is an average or a mean of this group, and an average of this darker group as well. Then the difference between the averages of the brighter group and the dark group is the contrast. We can also have darker count and the brighter count. For instance, if we want to count the white pixels, all the pixels with a gray level higher than the threshold is considered white. So if we count all the pixels of this group, then that's the bright count. And similarly, the dark count can be obtained by counting all the pixel numbers in the dark group. The Insight Explorer software has a very powerful tool for histogram extraction. For example, in order to inspect any shot on this part, we have several histogram tools distributed in different areas. This is histogram 1 area, and we use extract histogram tool for this area. With this tool, the histogram information is analyzed and stored, and then we can cite the result by using corresponding functions. For instance, for threshold, we use this function, and the result is corrected here. For others as well, like a contrast, dark count, bright count, and average. And then we can compare the result with the limits we set. For instance, the average. We can compare this average result with the minimum and the maximum value we have set. And also, this one is the contrast. We can compare the contrast result with the minimum and the maximum we set here. And then we can determine whether the part is a pass or fail. Let's do a quick practice on histogram control. Here's a vision program 1414 running at machine 33. So we're going to look into histogram 1. Histogram 1 average and contrast. And this is the histogram 1 area. Now let's see the spreadsheet and highlight the extract histogram tool of histogram 1. Let's see. Here's the region of histogram 1. And take a look at the average control. And the maximum value is set at 120. Actually, at the initial release of this program, it was set at 100. Now, let's assume if it's at 100 and then see what happens. Okay, you can see the average is out. It's okay. The reason is that, well, we have to take a look, we'll see if there are any shot shots here. Actually, there's no shot shots, right? So the reason is because the lighting condition and the part surface condition, also sometimes the distance of the part from the part to the camera lens to the light source, they can all affect the grade level, so affect the histogram average.
since it is not because of shorts or any burn condition on the part surface. So we should actually adjust the histogram average to a little higher than the current average. And if we look at the highest control we can go, actually it can go up as high as 150, but we don't really have to do that. We want to stay as close. And the next thing we'd like to look is that the region. So this is a histogram 1, so its region is here, region 1. If we click on region 1, you can see we can actually, if we click again here, you can see we can actually adjust the region 1 easily. And so most of the regions are allowed to be adjusted easily, but some regions may be controlled and not allowed to be adjusted in some way, or can't be adjusted completely. That's because there's less need or no need of adjustment. For this one, sometimes the orientation of the part can be varied, and in that kind of case, you may need to adjust the region. So if the border of the region aligns, just slightly inside the part surface, then that is the best. Sometimes if it is if it goes beyond the part surface, if the region touches the background, okay, then let's see what happens here. So we can find that the contrast is out. So in such kind of case, like now the contrast is reading 110, right? So in such case, you can't just easily adjust the contrast value. Actually, the maximum allowed is can be as high as 80. So in this case, it won't even allow you to adjust to be higher than 110. We have to look at the reason why the contrast is out. This is because, some part of the region has fallen into the background region. So in that case, then we can adjust the region and so that it's just aligned with the part surface again. And then let's see the result. So now it is good again, and the contrast is reading less than 28. Let's take a look at the concept of blob and the relevant tool. There is a method in the software called blob extraction. In the blob extraction method, each pixel is considered as either black or white, depending on its gray level and the threshold setup. A blob then is composed of pixels that are of the same color. In this case, it's either black or white, and connected to each other. To understand better, we may take a review of a previous slide. So here's a histogram, and depending on the threshold value, the pixels are divided into two groups. One is white, and the other is black. Now, let's take a look at this image as an example. We see there is black in the middle and some gray here and white here. If we set a threshold to be very low, to a very low level, and then this pixel in the middle will be the only one considered as black, and those gray pixels will definitely have a higher gray level than this threshold, so they will be considered as white. So this black pixel in the middle is an isolated one and not connecting to any other black pixels. So this pixel is actually a blob. It is a one pixel blob. Let's come back to this blob side. So in the actual application, so we can set a region for the blob, and then use the extract blobs tool. And we use threshold control here, and we can set up allowed area, so like to compare the found blob area with the allowed area, and then we can make a decision whether to pass or fail the parts depending on the size of the area being detected comparing to the allowed area size. Let's perform a quick practice with a blob. So here it is an example of mode 1412, which runs at station 37. This is a normal part. We detect a shot around this rib and also around this rib. The existing shot samples shows that this rib is the place of first sign of shot. So here is the shot portion, and with the white blob on rib 2, the shot is detected. Now let's come back to the good part and take a look at the setup. Let's see the spreadsheet. Okay, here is the white blob on rib 2. Here's the area for this detection. Threshold is set at 225, and the allowed area is set at 10. So right now the area detected is 0. If we set that to 200, the threshold to 200, which is still pretty high, right? And then let's take a look. So now there are 18 pixels being detected, and it exceeds the allowed area limit, so the part is failed. It's failed. And you can actually see the detected area is here. So we know this is a good part, right? It's not a shot, and the region is reasonably placed close to the boundary. So what we can do is that since the area is so small, maybe we can just easily increase the allowed region to 20. Sorry, excuse me, and this will be passed. The other way of doing it is that we can keep that at 10, and we can adjust the threshold a little higher. Let's see, to 10. So right now, 0 pixels detected, and it is passed. Okay, so now if we come to see shot, it's still detected. There are lots of pixels over here, more than 1500. And another one is a tiny shot. So it is still, excuse me, sorry. Let's place the outcome on the tool. Now we can see the result of the blobs being detected. So we can see this one is detected, but okay, the problem is that it detected more area than the shot area actually. So what we need to do, we need to increase the threshold level, right? Okay, now let's take a look again. All right, now the blob being detected is right on the shot area, so this is a suitable setup. We'll take a look at another example for the application of blob. We'll still look at this part. We know we have inspection regions along the border and beyond the border. Now, we may also notice that we have placed an inspection region over here, and the shape is quite irregular. Why we have this region over here? So if we take a look at the shot case, we can see that the top portion is actually not shotted. However, this area has been shot. So we have to catch such shots. So here's the region setup, and if there's any shots on this surface, then the surface condition will become wavy, and there will be the black area showing up. And so if we use the black blob detection, then we can detect that. Also, you may notice there is a small portion here. That is because when shot happens, this white gray piece may be gone, and then it will have a black blob showing up in this area. So here's the detail. So if you click on this region, then we may be able to adjust the shape, size, and point distribution of this region. But since this region is actually accurately located and very critically important, therefore we may take away some of the adjustment freedom in the future. Now let's take a look at the parameter setup for the blob detection, a black blob for region number 3. So we can see the threshold is set at 70, and it can actually be adjusted between 65 and 100. And the blob area limit is set to 5. So if a blob area is detected between 0 and 5, here's the area result. Right now it is 0. So if it is between 0 and 5, it will be passed. Actually, the maximum allowed area can be as high as 10, but we don't set it to the highest if we don't have to.
Let's take a look at the concept of pattern and its relevant tools. A pattern is a unique combination of geometric features. The pattern tool is very useful in locating the features and also in inspecting parts. When we define a pattern, we'd like to follow the standard with 4 requirements, which are clear, clean, unique, and unambiguous. These 4 requirements are abbreviated as CCUU. And so here is an example. This is a part with a flap portion here. With proper lighting condition, this flap portion can appear as white, and the background is black. And the shot area is starting from this edge. So it will be important to locate where this edge is. We'll start with the pattern tool as the locating tool, and let's see how to define this pattern. So there are these 4 possible solutions here. So the first one, we use segment in the short area as the pattern. But this one, if we use the requirements to judge, it will be good on clean, clear, but not good on unique and ambiguous. This one, if we judge, then it is clear but not clean because of here, and it is unique and unambiguous. And this one, it is clear, clean, unique. However, it is not unambiguous. Why? Because the scale is still not determined after that. Well, this one, it is clear, clean, unique, and unambiguous. So that's the best among the four. But the question, okay, you may ask a question why it is unambiguous. No, because it has the location, orientation, and the scale all determined after this pattern. Why the scale is determined? Because you see there is a small line segment here and a line segment here. These two are almost parallel, right? And then there is a distance that can be measured between these two line segments. And then since the distance can be determined, so the scale is determined. All right. So in the actual application, we may see, the block like this. And so there are several tools involved, but the most essential tools are trend pattern tool and also the find pattern tool. So the first step is to train the pattern. To train the pattern, we have to check out this enable training tab, enable training block over here. So then we will define the train region just like this. The train region is defined in red. And then we will click on the train pattern tab. We'll click on here, and then the pattern is trained and completed. Then after that, we'll need to find the pattern. So in order to find the pattern, you need to make sure that the search region is good. So the search region need to cover the pattern. So at least like this big, but it's still insufficient because the part location, the feature location can be varied from part to part. Okay, so the search region need to be sufficiently large to cover the possible location of the pattern. And then once all these are properly defined, then you will see the result of the pattern search here. Okay, and typically you will find a minimum score requirement over here. So we usually require minimum score at 75 and above in order to use a pattern to judge whether the part is good or bad. Actually, in such case, you may even have to define the score to be even higher than 75 to be more reliable. However, the pattern can be used in locating the features. In that kind of case, the minimum score can be as low as like a 50. Okay, can be even lower in some more difficult cases.